Hello fellow enthusiasts, and welcome back again to my channel. Today we're going to be looking at the LED blinker using the 555 timer. Later on we're going to be looking at the actual design on a breadboard, and then on the second part of this video for next week we're going to be looking at the same LED blinker using the Node MCUs, ESP8266, and ultimately we're going to condense the circuit into an AT tiny. Alright, so without further ado, let's go into this explanation. I'm going to take you through the tutorials of the basic, and then we're going to go and demonstrate the video of the actual circuits that we built. Alright, what you see here on the left hand side of this circuit are two operation amplifiers. We call them op amp 1 and op amp 2. At the middle you have a flip-flop. We haven't talked about flip-flops much, but we're going to look at them in a subsequent video when we come back in 2 weeks time to talk about the basic components that we didn't cover earlier on. These will include the flip-flops, the inverters, which is right here. I'm going to highlight it in a different color. Let me circle it with blue. So this we'll be talking about next week, and this also. So the inverter and the flip-flop and inverter. This is not your AC/DC inverter, but this inverts your digital signal from 1 to 0 or from 0 to 1. It changes the input state to the opposite between 1 and 0. Okay, we're going to be looking at this in 2 weeks time alongside the other symbols. Right, we're going to be looking at all the electronic, most electronic symbols. So this will come in 2 weeks time, because next week we're going to be looking at the microcontroller version of this LED blinker and how to condense that into an AT tiny saves components. Alright, so right here on the left hand side you have two comparators. The function of a comparator, again, I think we have to do more service to that. Let's add it to what we're going to be doing in 2 weeks time. But how a comparator functions in a general sense for today's purpose is that it has two inputs, the inverting and non-inverting input. The positive input is the non-inverting, the negative input is the inverting input. Whatever voltage that you have at the input, they will be compared between inverting and non-inverting. If they are equal, the output is 1. If the non-inverting is higher, the output is also 1. So the output is 1 as long as the inverting, the positive input, non-inverting, sorry, is greater than or equal to the negative input. Then the output. So why don't I just draw a table? Okay, let me use a table to illustrate this. It might be better. So input, output. If the input is greater than or equal to, if the positive input is greater than or equal to negative input, the output is 1. If the positive input is less than negative input, the output is 0. Okay, this is the logic. Bear this in mind whenever you work with a comparator. So let's go back and look at here. There are 3 resistors. Remember we talked about resistors as voltage dividers. Please watch that video if you missed that. Because we have equal resistors and they're connected in series between pin 8 and pin 1. Pin 8 is the VCC, the voltage supply voltage of this 555 timer, and pin 1 is the ground. When you have the voltage across the positive input, the power supply and ground, and you have equal resistors connected, you're going to have the same current flow in series and the same amount of voltage dropped across each resistor. Here we have 3 equal resistors of 5 kilo ohms each. So it will be the voltage supply divided by 15 kilo ohm resistor will give you the current, and then that value of the current multiplied by each resistor will give you the voltage across each resistor. And the voltage of this 5 timer is from 5 to 15 volts. Alright, so let's use this table here as a rule of thumb as we go through this illustration. Let's make it a little bit smaller. Okay. Now, I hope it's not too small for you. Out of the 555 timer, pin 1 is ground, 2 is trigger, 3 is the output, 4 is reset, 5 is voltage control or control voltage, 6 is the threshold, 7 is discharge, and 8 is the power supply voltage. So back to the internal configuration of the 555 timer, pin 6 is the non-inverting input of op amp 1, and pin 2 is the inverting input of op amp 2. So we're going to use these two to determine the logic, the output logic of the two internal op amps. Since we don't have access to the inverting input of op amp 1 and the non-inverting input of op amp 2, we're going to rely solely on pins 2 and pin 6 to control the internal logic of the system. Here is a basic diagram of the Astable Multivibrator using 555 timer, or you can call it a lead blinker. Here we tied pins 2 and pin 6 together as we mentioned earlier on, because this is the only way we can control the internal logic of the two comparators. When you power the circuit on, momentarily this capacitor C is going to be short. Remember, we talked about this in the tutorial on basic components. Please look at capacitors again. Momentarily it will short, and when it does that, pin 2 is grounded, so also is pin 6. When this happens, the non-inverting input of op amp 2 is higher than the inverting input of op amp 2, and the output of this op amp is going to be 1. When it is 1, the flip-flop here will be set. The S means set and R means reset. So this op amp, this flip-flop will be set. When it's set, what it means is the output will go high. There are two outputs in the flip-flop. There is a Q output, which is the normal output, and then the not Q output, which is the inverted output. In the configuration of the 555 timer uses the not Q output to connect to the load or the output. So when the flip-flop is set, the not Q will be 0, and when it is a 0, the inverter here will invert that state from a 0 to a 1, and the output will be high. And let's check what happens to pin 6 at that moment. The time that pin 6 and pin 2 were grounded, it guarantees that the positive input of op amp 1 is also lower than the negative input of op amp 1. And in that case, the output is 0. And because it's 0, it cannot reset the flip-flop. That state remains true, and since pin 3 is high because of the internal inverter here, since it is high, the C, capacitor C, is charged through R, and this charges until it goes from just less than 1/3 VCC all the way to 2/3 VCC. When it charges to 2/3 VCC, what happens? When 2 gets to 2/3 VCC, that means the inverting input of op amp 2 is higher than the non-inverting input of op amp 2, because our inverting input of op amp 2 is 1/3 VCC. Remember, we have 3 equal resistors. When the inverting goes higher than the non-inverting, the output goes to 0 0 here, but it does nothing for the flip-flop. By the time that pin 6 gets to 2/3 VCC, it guarantees that the non-inverting input and inverting input of op amp 1 are equal. Remember, by the table, if they are equal, the output is high. So this output is 1, and which is used to reset the flip-flop. When this is reset, the Q output is 0 and the not Q is 1. When the not Q is 1, the inverter flips that over to 0, so the output will now turn off. So that's how you're gonna get the continuous duty cycle on and off, and this is determined by the value of the R and C. So the frequency is a function of R and C. Okay, and that's the way it continues, the cycle continues. Alright, so this pin here goes to the control voltage, so you can add external voltage here to increase the value of the voltage here, such that so you have access, let's put it that way, you have access to changing the value, or the threshold value, or the triggering point of op amp 1 through pin 5. So if you add an additional voltage here or a capacitor, you can modulate the output, because you can change the triggering point. You can delay it a little bit, or you can make it a little bit faster by the value that you connect here. Think about it, internally you have 10 kilo ohm here, so if you connect a resistor, play around with this, connect a resistor from this point to ground, from pin 5 to ground, such that the parallel value will change the value seen across the inverting input of op amp 1 and the non-inverting input of op amp 1. See how that goes. You get a modulation of the frequency of the system you designed from here. Okay. Alright, let's go quickly and look at other circuit that we built around this 555 timer LED blinker and what else we can do with it.
On the left hand side you have the low frequency Astable Multivibrator. On the right hand side you have the audio frequency Astable Multivibrator. Now we have a speaker we're going to connect to the audio frequency Astable Multivibrator. As you can see, the audio cuts off when the LED is off, and turns on when the LED is on. So we're controlling the pin 4 of the audio frequency Astable Multivibrator directly from pin 3 of the low frequency Astable Multivibrator. A little modification we did here, we included a variable resistor to the low frequency Astable Multivibrator, so we can change the duty cycle. So we connected this resistor in series to the 1 kilo ohm resistor, so we can vary the value.
Now right here we've built two 555 timers, one on the left hand side a low frequency 555 timer, and one on the right hand side a higher frequency or audio frequency 555 timer. Now on the left hand side you have the low frequency 555 timer, and on the right hand side you have the audio frequency 555 timer. We're going to use the left hand side to modulate the right hand side. Now find the value of your R, so we're going to call this R1 C1, and on this side we have R2 C2. Find the value of R1 C1, that will give you a low frequency 555 Astable Multivibrator, let's call it that, and the value of R2 and C2, that will give you an audio frequency Astable Multivibrator. To do this, we've put the circuit diagram here. Take the output of the left hand side to modulate the right hand side. Remember, pin 4 is the reset pin, so when you connect pin 3 of the left hand side directly to pin 4 of the right hand side, remember to include the pull-up resistor of 10k. When you do that, when the left hand side is high, because the reset pin is a low, is a negative, takes a negative voltage, and you have the output high of the left hand side. It allows the right hand side to run, and you can see the frequency of the right hand side right within the on time of the left hand side. When the left hand side goes low, it will pull down pin 4 of the right hand side, and you will hear crickets from the right hand side. Nothing, right? And then it will repeat. Also, you can use a transistor as a switch. Remember, we talked about transistors as a switch, or transistors as switches, or transistor as a switch. Go back to the tutorial on that and look at that one more time. However, we're just going to talk about this in passing. When you use transistors, when the output of the left hand side is high, this transistor will be turned on and basically shut the collector to the emitter, and you're pulling down pin 4 of the right hand side circuit. At that point, you hear crickets from the right hand side. Nothing. But then when the output of the left hand side is low, the transistor is open, and you allow the left hand side to oscillate, the right hand side. When the output of this of the when the output of the left hand side is low, the transistor is open, and the pull down on pin 4 is now restored, and at that point you have an oscillation on the right hand side, so you can hear the audio frequency from the right hand side. So I'm going to demonstrate this shortly, but these are just the basic things that we want to show you today. So that will be it from us today. Thank you for watching, and remember to subscribe, tell your friends about this channel, and keep coming back. Give us your questions or your tutorial ideas, and we'll do our best to address those. Alright, so like I said earlier on, next week we're going to be looking at part 2 of this using Node MCUs or microcontrollers, and the week after that we're going to do component symbols, electronic component symbols. We can also look at inverters and comparators and flip-flops. Yes, and we're going to look at the electronic symbols, the ones that we didn't touch before. We're going to look at many more, so you can build up your backgrounds or your repertoire, or if you like, or your electronic vocabularies. So we're going to look at all those. Please remember to keep coming back. And I remember a few years ago when we actually several years ago, when I finished my first degree, and we were working at Katsina Steel Rolling Company with my friends like Kenny Fine, Andrew, Steven, many of us. We were like 34 of us then. So we built this circuit for the company called Electronic Signpost. It was one of the first in that region in those days. We built the clocking system was basically based on 555 timer. We used a decade counter to advance the clocks and the controls from transistor switches and relays and turn on the lights and all that. It was amazing. We built that solely from hardwired things. And now we can do a lot more with microcontrollers. We didn't have as much access then to microcontrollers, and they were even a little bit more expensive right then. But now we can do a lot of these things using Node MCUs. We can even do AT-Tinies. So these amazing things have changed. So please keep coming back to us. We're going to show you these things. We're going to demonstrate some of these things that you can build on your own with just few components on a Saturday afternoon like this. Alright, thanks my friends, and keep coming back. Don't forget to subscribe. I can't say this enough. I do this tutorials because I like to do it, but also if you like what you're watching, please share, invite your friends, let them watch. If you have anyone who's at the university who's learning electronics, this could be a good place to start. Alright, I'm speaking to you directly because I know when I was doing my bachelor's degrees, I didn't have much access to the tutorials or to the materials, right? So I was just going by what I read in the books, and we didn't have enough item to come here. We can inspire them and support them and challenge them. I know when I was growing up, I didn't have access to some of these things. The internet was not very rampant, and the data cost was very expensive. But now you have access to data and so much at your disposal. All right, so with your data, the time you spend on Facebook and social media, you can use some of them for learning. Just a fraction of the time you spend on social media, you can use them for learning. Come to my channel. If you're an electronic engineer or electrical engineering student, electronic engineering student, or computer engineering student, I encourage you to come to my channel. Right, if you're a hobbyist, I also encourage you to come to my channel because there's a lot to learn. All right, so I just saw something in this circuit and I thought I should mention something about it. And so what we're gonna do in a couple of weeks time, we're gonna look at drawing electronic circuits. Yes, we're gonna look at that, drawing electronic circuit, the right way to draw electronic circuit. So I'm gonna, maybe in 3 weeks time, because we have things lined up for the next 2 weekends. So in 3 weeks time, we'll try to squeeze it in within the week if time permits, but let's look at 3 weeks time and we'll try to figure out how to squeeze it in earlier. But if not, in 3 weeks time, we're going to be looking at how to draw electronic circuit diagrams. Very, very keen and important, and it will also help you in reading electronic circuits. So my friend who had asked me to do a tutorial on how to read and understand electronic circuits, and I'm going to dedicate that to you one more time. So next week we're going to do second part of this video. The week after that I'm going to dedicate to you, and also the week after that. How about that? So I want to make sure that we cover all the basics, and I will see you in my next tutorial. Bye bye.
Now the duty cycle is longer, so the audio alarm stays on a little bit longer, but when it goes off as well, it will stay off a little bit longer as well. Now it's gonna stay off a little bit longer. As long as it stayed on, it will also stay off that much, and the cycle will continue. Yep. So now I'm gonna vary to change the duty cycle. And you can change it back gradually. A little bit more. And a little bit more. Right, so I'm gonna shut the resistor, 1 kilo ohm resistor, so I can control it directly with the resistor. So the value of the resistor determines the duty cycle or the frequency.